Hi, my name is Melanie Gurunathan, and I would like to welcome you today to my presentation. I will be discussing the exciting way that Toyota Research Institute, TRI, is using executable UML in order to help advance autonomous driving development. Instead of discussing our design, I will approach this presentation from a different perspective. Initially, I'm going to focus on the problem we are solving with executable UML. Next, I will cover what skills our team brings to the project and how we brought a fellow engineer up to speed so that he could successfully contribute. Finally, maybe most importantly, I want to share how TRI is using Shlaer-Mellor methodology separate from the commercial product, yet still providing value to different parts of the organization. Let's start with our project. I thought before I jump into the specifics of the project, I would give a brief overview of what my company does. TRI is a research institute with the goal of building innovation to improve the human experience. The project that I will discuss today is focused solely on the field of autonomous driving. However, TRI does several other areas of research. We design robots to enhance human abilities, study material science, including projects advancing battery technology, and use data to better predict human behavior. Our division develops automated driving through two main initiatives. Chauffeur is our autonomous driving application, in which vehicles navigate complex road scenarios with a safety driver as backup. This application was recently being tested to safely maneuver the roads of Tokyo during the 2021 Olympics. Our Guardian project aims to enhance vehicle safety. It looks to augment the driving experience by working with the driver. For example, if you're driving home late and start to drift out of your lane, a feature of Guardian could be to detect your drowsy state and get the vehicle safely to the side. Our challenge at TRI is to systematically define and assess competent driving behavior regardless of the complexity of the roads being navigated. Unlike my previous experiences using executable UML to create commercial products, at TRI we are using Shlaer-Mellor technology to build a functioning reference model of how a vehicle navigates its environment. At a previous company, I had the opportunity to serve as a program manager. While this role was a very interesting experience, one key benefit was that I was exposed to how different areas built in quality and safety into the product. One example was the manufacturing team had boards that would undergo additional test scrutiny, and if they survived, be marked as known good boards, the gold standard. Boards manufactured after that would be tested against this known good board. This was an intriguing concept. It served a purpose of identifying and weed out boards which the manufacturing process failed, causing variation in performance, but it didn't catch design issues. What I love about our reference model is that it can compare and find variation, but because it's implementation independent, it can also find design issues. This means our reference model reflects how a vehicle should navigate its environment, no matter how it's controlled or designed. So our approach to building a reference model was to fully define the vehicle environment with subsystems like road, intersection, crosswalk, and lane reconfiguration. Then the ego vehicle subsystem would be used to navigate these elements. What we found was that the models, without being implemented into code, provided immediate benefit. We realized that many teams did not have consistent vocabulary for discussing scenarios. Some teams adopted our class names to provide this precision. Another team working on scenario language plans to use aspects of our state machine in their planning. Additionally, we found that we could use our models to provide insight on feature test coverage. One big win that is consistent with all executable UML projects is that with minimal training, subject matter experts can read a class model and suggest classes that may be missing or relationships that require updating. This makes our design better, but it also provokes great conversation that can lead to better requirements and testing. From my experience, this is much harder with other design approaches. many code reviews will have very little contribution from outside stakeholders. Now that I've explained the what, let's talk about the who. What brought me here to talk to you today was a lot of hands-on experience making executable models run. Before automotive, my career spanned decades working on medical devices for large corporation to a small incubator. At St. Jude Medical, we designed implantable cardiac devices in executable UML and then hand translated them into assembly. Later, on a next-gen project, we designed an implantable system in Bridgepoint and then used model compilers to generate code. My next company used other modeling techniques to implement a complicated robotics system. Here I learned the importance of spending time to design a system. I watched how hard it was to add a second bedside panel because there was no panel or button class to populate. Being sold on the importance of good design, I spent a decade working in an incubator, building lab apparatus to test ideas, GUIs and embedded systems, databases to help organize scientific data, even a reusable wireless communication system with a base station and an RF domain. All of these projects were fully defined in executable UML. Many of you may know Leon Starr. If not, you may have heard him in the conference's keynote speech. Leon recruited me to TRI to work on model-based systems engineering in this relatively young industry. He had started the models, but wanted to realize them to code. As Leon was refining his models, I began planning a proof of concept to show management. We selected a small feature and worked on implementing it into code. We also needed to determine the best way to hook into the mainline product. We decided to drive the models using logs from our fleet. Once we could show that, we realized there was too much work for the two of us. Management allowed us to add a team member from existing employees. At this point, we had a challenge. Currently, our team was small but had lots of executable UML experience. Finding and training the right engineer would take away from advancing the project. Leon started to offer a basic Shlaer-Mellor class, which also served to educate our peers on the type of work we were doing. One engineer from our team seemed really engaged and interested in the technology. He was curious on how we had applied it to autonomous driving. Thomas ended up being a great addition to our team. His contribution to systems requirements, as well as his vast knowledge of industry regulation and standards, allowed him to challenge the design. His existing relationships outside of the group allowed him to advocate for the methodology. Lastly, our models contained a large amount of dynamic data, and as we approached more complicated scenarios, we identified a need for tooling to support our effort. Since our building environment involved many of his existing tools, we were able to recruit Andrew Mangonia as a contractor. Not only was he able to mentor Thomas, but he was able to apply experience from other projects to approach our tooling needs. So this is our lean team. I wanted to share a little more about my experience training a new team member. One challenge with our methodology is the amount of knowledge needed to be able to contribute. Finding someone within the team can seem a bit overwhelming. I thought I would share our approach. We started with the fundamentals of the methodology. In our case, we were lucky to have Leon's experience in teaching classes. We also suggested a few books. Next, we took the time to run through some implemented examples. Doing this, we were able to set up their environment, plus it's a way of setting expectation of what is to come. Since our immediate need was translation, I started by giving him a state to translate from action language to code. He started with 1 or 2 line states, then took on more difficult actions. This made him more comfortable with the action language, but also had him consulting the class model as he navigated through relationships. Eventually, he was ready to implement a state machine, which included implementing events and transition tables. Compiling his code allowed him to better understand the translation process, and soon he found patterns in his translation errors. We moved on to domain operations, as these would become the entry point to the models during the testing phase. Developing testing was our last step to see how well the individual understands the model and also teaches them how to debug at a higher level of abstraction. It was often a challenge to determine whether something was an implementation versus a design issue. During this phase, we did a lot of buddy coding to work through failing test cases. Sometimes the interface needed updating. Sometimes delayed events were not being canceled appropriately. For each solved problem, I was impressed that he did so by reviewing logs instead of going down to the generated code. Next, I will discuss the how. More specifically, the tooling decisions we made to take the models to code. Though there are different tools available to accomplish this task, I wanted to share what we use at TRI and why. Due to the size of the team, it was important to make the process simple and automated as much as possible. We also chose to save our work in text-based formats as much as possible so that we could quickly identify changes. We decided to go with open source tools when available in order to keep our project costs down, but also to facilitate collaboration in the future. In this slide, it is important to note that black arrows are manually performed, whereas red arrows are automated through tooling. With such a small team, automation is essential. Originally, we looked at a few drawing tools, but we initially settled on Lucidchart as TRI held licenses. Due to the lack of versioning and proprietary file formatting, we knew it wasn't the final solution. Recently, we moved to Flatland, which stores as text, creates nice-looking drawings, and builds easily into our process. We are keeping our code and documentation together through the use of literate programming. This helps us ensure that our documentation and code stay in sync. It also allows us to generate attractive, exhaustive documentation with or without code. We are translating our design into model realization's Mika code and running it through the Bosel test harness. In the top right of the side of the slide, you will note two inputs to the test suite. Originally, tests are hand-coded to test the completeness of the design. Once you believe your design is working adequately, the models can be driven through tooling that translates logs to test cases. To demonstrate the power of these generated outputs, here's a video showing a generated sequence diagram driven by actual vehicle data next to its corresponding vehicle log. The vehicle is performing a single lane change. Note, despite a simple case, we detected a scenario where a vehicle crossed the lane division before signaling for the full 2-second minimum requirement. As it plays again, you can see the model acknowledges the deviation and continues with the maneuver. The final topic is how to apply this reference model. Now that we have an approach to model and implement our vehicle guidance domain, what use can it serve? Earlier, we covered the benefits of the model itself. Now I want to take a few minutes to discuss some of the challenges we have faced with its implementation, plus propose a powerful use for our product. Every project has challenges. I thought I would share some of our main challenges and ideas we have to combat them. First of all, we are currently staffed at about 2.5 engineers due to other commitments. With these resources, we must push the model scope forward, improve our integration with other teams, and continue to sell the project up. Luckily, we were able to get skilled contractors to assist, and other than that, we're trying to have a solid process and automate as much as possible. Secondly, this model has a unique challenge. As the vehicle navigates through its environment, you can imagine there's a lot of dynamically updated data. Groups of instances being added and deleted. So far, pulling in pre-populated instance sets has worked, but it isn't a final solution. We are currently working on a tool which will interface with the domain and manage timely data updates. Finally, how do you know when your feature is complete? You can suggest testing more vehicle data through the design. I would argue the best approach is many eyes on the problem. Recently, TRI has approved the open source release of our design. Since executable UML is a unique approach to MBSE, we are hoping that once released, Other automotive systems engineer teams will be interested in collaborating with us, and who knows, maybe a few of you will be interested in the problem and we'll take a look. As we come to the end of this presentation, I would like to propose a potential application for our platform-independent vehicle guidance domain. Recently, Woven Planet, a fellow company under the umbrella of Toyota Motor Corporation, acquired Lyft's autonomous driving division. You can imagine we asked ourselves, wouldn't it be cool if we could run TRI and Woven's autonomous vehicle logs through our reference model and compare approaches? We can take this one step further. With the move to open source, it would be great to mature our design enough to be an industry gold standard that other companies could use as a part of their testing strategy. We aren't there yet, but who says we can't look ahead? Thank you for taking your time to listen to my presentation on the use of Shlaer-Mellor methodology in the field of autonomous driving. Please connect with me on LinkedIn. I plan to use this venue to share information about TRI's open source project release. Now I welcome any questions.